We now discuss the solution of a problem from the section Algebra. The problem is on the greatest common divisor from number theory, and this question has appeared in CSIR National Eligibility Test held on 30th November 2020, and it is from the section C. The problem is for positive integers m and n, let GCD bracket m comma n denote their greatest common divisor. Let m greater than n be such that the GCD of m comma n is 1. Then which of the following statements are true? We are given 4 options. Option 1, the GCD of m minus n, m plus n is equal to 1. Option 2, the GCD of m minus n, comma, m plus n can have a prime divisor. Option 3, there exist integers x, y such that nx minus my is equal to 3. Option 4, the GCD of m minus n, comma, m plus n can be an odd prime. So we are given 2 positive integers, that means 2 natural numbers, and m greater than n such that GCD of m comma n is equal to 1. Then we have to decide of the following 4 which of them are true statements. Let's now discuss the solution of the problem in detail. We have mn belongs to n, the set of natural numbers which are positive integers, m greater than n, and GCD of m comma n is equal to 1. This is the condition. The condition is m greater than n and the GCD of m comma n is equal to 1. Let's now decide the truth of the statements given in options 1 and 2. Option 1 says the GCD of m minus n, comma, m plus n is 1 for all mn satisfying these 2 conditions. Is it true? If it is true, we have to prove that it is true for all. If it is not true, then you exhibit a pair of natural numbers mn satisfying this condition. And the second one says this can have a prime divisor. Can have prime divisor means you exhibit a pair of natural numbers satisfying this condition for which it has, this GCD has a prime divisor. So we will show by means of the following counter examples. Let m is equal to 3 and n is equal to 1. Now m greater than n, obviously, the GCD of m comma n, that is the 3 comma 1 is 1, and the GCD of m minus n comma m plus n is the GCD of 3 minus 1 comma 3 plus 1, and that is the GCD of 2 comma 4, and the GCD of 2 comma 4 is 2, which is not equal to 1. So this tells you that there exists a pair of elements mn satisfying this condition for which this is not true, and hence option 1 is not true. And further it says you have a pair of elements for which this condition is satisfied, for which the GCD of m minus n and m plus n has a prime divisor, namely 2. So the same counter example works for both these favor. So this says this is possible. This is possible. Can have means it can have for some elements. So, and the GCD of m minus n comma m plus n has a prime divisor 2. So the option 1 is not true and the option 2 is true. Why? Because it says can have means for some pair of elements this can happen. Yes, it is. So that is the option 1 is not true and the option 2 is true. Now let's get into the next option, option 4. GCD of m minus n comma m plus n can be an odd prime. Can be an odd prime. If you want to show the GCD of this is an odd prime sometimes, that means you have to exhibit some pair of elements satisfying this condition for which the GCD has an odd prime. Or else for all pair of elements mn belongs to n satisfying this condition, the GCD of m minus n and m plus n is not an odd prime. Not an odd prime. So let's see. We will see the general case. So let D be the GCD of m minus n comma m plus n. We are going to show that D is not an odd prime. So this means D divides m minus n and D divides m plus n. This implies D divides their sum m plus n plus m minus n and D divides their difference m plus n minus m minus n. This implies D divides 2m and D divides 2n. And this implies D divides 2. Why? Because the GCD of m comma n is 1. So this implies D divides 2 means D is either 1 or 2. That means the GCD of m minus n comma m plus n have only two choices, namely 1 or 2. So it will never have an odd prime. So thus we have proved a general result. This result is if mn are natural numbers, m greater than n, the GCD of m comma n is 1, then the GCD of m minus n comma m plus n is equal to 1 or 2. So it says the GCD of m minus n comma m plus n can never be an odd prime. So the option 4 is not true. It may be noted from this general result, the option 1 is not true. Why? Because this result says this is equal to 1 for some choice of m and n. And the option 2 is true because for some choices this is 2. That is, the GCD has a prime divisor. So from this result you can establish that the option 1 is not true and the option 2 is true. Let's continue. We have this, and the option 3 is there exists integers x, y such that nx minus my is equal to 3. We will establish this result. Now, we have GCD of m comma n is 1. Then we know that there exists integers x naught, y naught such that mx naught plus ny naught is equal to 1. Multiply throughout by 3. That will imply 3 times mx naught plus 3 times ny naught is equal to 3. This implies n times 3y naught minus m times minus 3x naught is equal to 3. Yeah, it is same as this. That means this implies nx minus my is 3, where x is 3y naught belongs to z and y is minus 3x naught belongs to z. Thus we have proved there exists integers x, y such that nx minus my is equal to 3. Thus we have established the option 3. This proves the option 3 is true. So finally, what is the answer for this question? The answer is the options 2 and 3 are true and the remaining 2 are not true. So that is the discussion of the solution of the problem from the section Algebra, and the question is on the GCD, greatest common divisor. And this is an interesting problem, and go on working out some more problems from algebra from the section number theory, and I wish you all the best. Thank you.